Today we want to solve the crystallographic inequality, and it says the following. Given n non-negative real numbers, pk, that satisfy the following condition, which is that they all sum up to 1, then given a function g of x, which is the summation of pk times cosine of beta kx, where these beta k's are real numbers, then we have the following inequality, which is that g squared is smaller or equal to 1/2 times 1 plus g of 2x. Okay, how do we prove this inequality? Let's go about it. So we need two facts. The first is a derivation of the cosine formula. So just that the cosine squared of beta kx is equal to 1/2 times 1 plus cosine of beta kx. Oh, there's a 2 here. That's what we want. Okay, how do we know this is true? Let's start out with the following. Cosine of 2 beta kx. This is the same thing as cosine of beta kx plus beta kx. Well, and here we can use the cosine formula. This is basically cosine squared of beta kx minus sine squared of beta kx. Well, and sine squared of beta kx is the same thing as 1 minus cosine squared of beta kx. Okay, so this minus will flip. This minus here is going to flip the plus 1 into minus, and we'll flip the minus cosine into a plus. And then we have 2 times cosine squared of beta kx minus 1. Okay, so we have this side and this one, and now we want to solve the formula for cosine squared. We move the 1 to the left-hand side, and we have cosine of 2 beta k x plus 1 is equal to 2 times cosine squared of beta kx. Then we divide by 2, and then we have our formula that we wanted. Okay, and just to recap, what is this cosine formula about? We have cosine of alpha plus beta is equal to cosine of alpha times cosine of beta minus sinus of alpha times sine of beta. Yeah. Okay. And in our case, we used just for alpha and beta the beta kx. Okay, let's keep going with our second fact that we want to use, which is that the function phi of t equals t squared is convex on the real numbers. What does it mean? So basically, if we want to use a graphic interpretation of what this means, this would be a function that always points upwards. Basically, if you could pour water you can view it like some sort of a container, and if you put water in it, it will not slip anywhere. So you have just yeah. Okay. That's basically roughly the idea of it. That it always points upwards. It has negative convexity, negative curvature. In terms of just like a rigorous definition, we have for all x1 and x2. Well, let's actually use x and y for all x and y in the real numbers. Of course, it's just because it's convex in the real numbers. I mean, if it was convex in a smaller space, then you would have to choose that according space. And for all lambda between 0 and 1, we have the following inequality. Phi of 1 minus lambda times x plus lambda times y is smaller or equal to 1 minus lambda times phi of x plus lambda times phi of y. Okay, so what do we have here inside of this argument? This is basically a connecting line between x and y, and you can view the lambda as like some sort of a parameter or a timeline from 0 to 1. And if we insert a 0 into lambda, we get x, and if we insert lambda equals 1, then we get y. So it's called a convex combination. Let's give it a number, and let's mark it somewhere here. For example, if we have an x here and then we have our y here, then that entire line would be exactly this number 1. But of course, we're not just taking this convex combination, we're also applying the function phi on it. So if this is here, this point, then this would be the entire left-hand side. So this is the function phi applied to this phi of this one, applied to this convex combination. It would give us this entire arc. Let's take a look at the right-hand side. What do we have here? We have here a convex combination between phi of x and phi and y. If we insert a lambda 0, then we have phi of x. If we insert a lambda 1, then we have phi of y. Where is our phi of x and phi of y? This is here our phi of x, and this here is phi of y. Okay, and what is this convex combination? That's basically just this line between these 2 points. Okay, and the statement now is that when we take the convex combination of these 2 points, x and y, and then apply the phi function, then we end up at a value that is smaller or equal to the function applied to these points, and then you taking the convex combination of them, which is roughly the same idea as the water example, that it doesn't that we don't lose any water in the container. But yes, so this video is not about convexity. We do not want to revisit the concept or prove anything about it. We just wanted to just recap quickly. In any case, if a function is convex, then this function fulfills the so-called Jensen's inequality, which says the following: phi of the summation from 1 to n, pk times xk is smaller or equal to the summation of pk times phi of xk from 1 to n. Well, okay, so this is basically, the Jensen's inequality is just the generalization of the convexity property, just with not 2 elements, but with n elements. So if we take, for example, in our case, in our previous convexity example, the 1 minus lambda would be our first P1, and the second one would be just lambda. Okay, so Jensen's inequality. Okay. Yeah. Provided that these pk's are equal to 1. Yeah, and as we're going to see, that's a condition that we also placed for our example, and that's very good. Okay. Good. Let's apply this. We use, for our xk, the cosine of beta kx. So let's see what happens. So the phi we said is just the squaring. So let's take that. This is the summation of pk times cosine of beta k x. So this is just squaring, because, like we said, the function phi is nothing more than just the squaring. Oops. N. And the right-hand side is the summation of pk times phi of xk. So the xk is the thing that is being squared. Okay. Oh, actually, we forgot something to mention something, which is that this this thing here in the inside is g of x, if you can recall. That's exactly how we define our g of x, which we want to prove the inequality for. Let's go back to our proof. So we have here g of x squared. Okay, so this is smaller or equal, according to our fact number 2, summation of pk from 1 to n of cosine beta kx, and this is of course squared. So maybe we want to mark it as well. Let's give it a mark, number 2, and here as well. So just to make it clear how we arrived at this point. Okay, so and according to fact number 1, this here is exactly the same thing as 1 over 2 times 1 plus cosine of 2 beta kx. Okay, let's use that and write, this is the summation of pk 1/2 times 1 plus cosine of 2 beta kx from 1 to n. So what we can do already is we can pull this 1/2 out because it's just a constant. And what we want to do is we want to multiply this pk with both terms in the bracket. So we have 1/2 times the summation from 1 to n of pk plus pk times cosine of beta k 2x. What we want to do now is we want to split our summation. So we have one summation for the pk's from 1 to n plus the summation from 1 to n of pk times cosine of beta k 2x. Well, and from our condition, we know that this here becomes 1, and this here is actually g of 2x, just like the g function just evaluated at the point 2x instead of x. Okay, so we have now here 1/2 times 1 plus g of 2x. Okay, so we started out with g squared, and then we showed that this is smaller or equal to 1/2 times 1 plus g of 2x. Let's go above and see that that's exactly what we wanted to show. And that concludes our exercise.